Imagine, the year is 1054 and an unusually bright star emerges in the night sky, outshining all others, even visible during the day. This supernova explosion, a massive star experiencing a core collapse event, leaves behind what we now know as the Crab Nebula, 11 light-years wide and still expanding. This celestial incident was documented by astronomers in China, Japan, and the Middle East, and later, the remnant of this explosion was rediscovered in the 18th century. But there is a conundrum. The mass of the Crab Nebula and its pulsar does not quite add up to the mass needed for such a supernova. And now, with the aid of the James Webb Space Telescope, we are uncovering fresh details and perhaps, just perhaps. But that's a secret yet to be revealed. Stay tuned, friends. What's up, my amazing and curious folks? Ready to unravel mysteries together? I'm your host Caesar, and by my side, as always, is the brilliant and effervescent Sonia. You're tuned into Curiosity Wonderland. Don't forget to subscribe and hit that bell icon to stay updated with our every episode.
Hello everyone. It's always a pleasure to be here with Caesar Chagas and all of you. Let's dive into today's curiosity, shall we?
Now, let's journey back in time, nearly 1,000 years ago, the year 1054. A new star appears in the night sky, outshining all others. It's even visible during the day before it fades away, disappearing for centuries. This was no ordinary star, my friends. This was the aftermath of a core collapse supernova explosion. With the invention of the telescope, 18th century astronomers discovered the remnant of this explosion in the same region of the sky. Over time, as our astronomical capabilities improved, we finally pieced together what was truly occurring. This once massive star underwent a core collapse event, dying in a supernova, and leaving a pulsing neutron star behind at its center. This remnant is what we know today as the Crab Nebula. The Crab Nebula continues to expand and evolve, now spanning an impressive 11 light-years across. Previous studies have revealed enormous stores of gaseous material ejected into the interstellar medium, about 5 solar masses worth. However, here's where the mystery begins. It should take at least 8 solar masses to trigger a core collapse supernova, but the material here just doesn't add up. But, the James Webb Space Telescope, or Jwst for short, may be our hero in solving this cosmic mass mystery. With its near-infrared camera and mid-infrared instrument, we are getting a superior view of the Crab Nebula compared to all telescopes that came before. New details are already appearing. It's truly an exciting time in astronomy, don't you think? The supernova of 1054 was visible during the day for about 3 months and remained visible in the night sky for a total of 2 years. 7 centuries later, the remnant of this explosion was rediscovered. This link between ancient and modern observations was finally established just over a century ago. The details of the initial explosion required looking back through worldwide records, since no Western or European sources recorded it. The first discovered source came from the Chinese Empire, where astronomers recorded what they called a guest star first appearing on the 4th of July, 1054. Quite a spectacle, wouldn't you agree? This astronomical spectacle didn't just capture the attention of Chinese astronomers. Sightings were recorded in Japan and the Middle East as well. The star remained visible for around 2 years before fading away below the naked eye threshold. This is quite typical behavior for a core collapse supernova. It swiftly rises to a peak brightness that's thousands to millions of times the brightness of the original star, and then gradually fades away over the span of months to years. Centuries later, the remnant of this ancient explosion was discovered by John Bevis in 1731. However, the connection to the 1054 supernova wasn't made until much later. Interestingly, back in the early 18th century, astronomers were more focused on nearby celestial bodies like planets, moons, and comets, rather than these mysterious smudges in the sky. So, Bevis's discovery went largely unnoticed until 1758, a significant year for astronomers. That was when Halley's Comet, seen previously in the years 1456, 1531, 1607, and 1682, was due to return, as predicted by Edmund Halley back in 1705. Coincidentally, during the search for Halley's Comet, Charles Messier noticed this object and initially confused it for the sought-after comet. It was a common issue back then, with 18th century quality telescopes, comets, nebulae, and other extended objects were not readily distinguishable from one another. To prevent further confusion, Messier started creating an astronomical catalog of objects, now famous as the Messier Catalog. The Crab Nebula became the very first object in this catalog, bearing the designation of M1 Messier 1. Now, it's been a whopping 265 years since its rediscovery, and the Crab Nebula continues to captivate astronomers. Some of its remarkable properties include being one of the closest core-collapse supernovae to occur in modern human history. At only 6,500 light-years away, it's possible to resolve individual features within it, including gas filaments and wind-driven ejecta. What's more, we can physically see the nebula expanding over time. Its core is powered by a fascinating stellar remnant, a young pulsar or a neutron star that spins around on its axis an impressive 30 times per second. How amazing is the universe we live in? The Crab Nebula is a marvel in the world of astronomy. It's a delight both for professional astronomers and amateurs alike. Anyone with a telescope can find it and observe it for themselves. With the right equipment, even a dedicated amateur can measure the expansion of this nebula over decade-long timescales. Isn't that incredible?
Wait, you're saying that even amateur astronomers can observe the expansion of the nebula? How is this possible?
Well, with the advent of accessible, off-the-shelf equipment, even an amateur can track and measure the expansion of the Crab Nebula. For instance, this nebula has been observed to increase in size by about 1/10 of a light-year between 2008 and 2017. That's the power of modern astronomy in the hands of dedicated enthusiasts. Now, let's talk about the properties of the Crab Nebula. Back in 1054, the supernova that formed the nebula reached a peak brightness that was equivalent to the combined brightness of 400 million suns. Today, nearly 1,000 years later, the nebula spans a full 11 light-years across, with the outskirts still expanding at 0.5% of light speed.
That's mind-blowing. But, can you give us some examples to better understand these numbers?
Sure. Let's take the speed of light, which is approximately 300,000 kilometers per second. So, if the outskirts of the nebula are expanding at 0.5% of light speed, that's about 1,500 kilometers per second. To put that into perspective, it's like traveling the entire length of the Grand Canyon in just a blink of an eye. In terms of its size, the nebula is now 11 light-years across. 1 light-year is about 9 trillion kilometers. So, the nebula is approximately 99 trillion kilometers across. That's like taking a trip around the Earth's equator over 2 billion times. With X-ray observations from NASA's Chandra X-ray Observatory, we're able to see the hot gases and plasmas created by the central pulsar. These observations have even allowed us to trace how these features change over time. It's like watching a cosmic movie unfold. Truly fascinating. When we take a multi-wavelength view of the Crab Nebula, we can see a variety of features and infer a large amount of information about the physical properties of this supernova remnant and the event that gave rise to it. The central pulsar, discovered only in 1968, is the young neutron star left behind by the supernova event of 1054. The pulsar is slowly changing in period, is merely about 10 kilometers in radius, yet contains a mass of about 1.4 times that of our Sun. The majority of light coming from the Crab Nebula is more energetic than what our Sun produces, making it the brightest X-ray source above a certain energy threshold in the entire sky. The material surrounding the central star emits a massive amount of ultraviolet light. If you added up all the light coming from the Crab Nebula, you'd find it still 75,000 times as luminous as our Sun. The Crab Nebula is also a cosmic laboratory. Many elements, including hydrogen, oxygen, silicon, and more have been discovered in it, providing evidence that many of the elements heavier than oxygen but lighter than zirconium are primarily produced in core-collapse supernovae. At lower energies, we find gaseous filaments, ejected jets of material, and ionized loops of gas. When combined into a single composite image, we see the true magnificence and diversity of phenomena at play in the Crab Nebula. Interestingly, this nebula arose from a massive star that died in a core-collapse supernova back in 1054. The event was so bright that it was visible worldwide, allowing us to reconstruct this historical event. However, despite all this fascinating information, there's still a problem that emerges when it comes to the Crab Nebula, the problem of mass. But we'll explore more on that later. Astronomers generally believe that a star's initial mass, the amount of mass that it has when it's born, is what determines its eventual fate. This is largely accurate. Stars like our Sun, which typically include stars between 40% and 800% the mass of the Sun, follow a specific life cycle. They burn through their core hydrogen, evolve into red giants, begin fusing helium in their cores, and then gently die, blowing off their outer layers into what we call a planetary nebula, while their cores contract to form a white dwarf. The lowest mass stars, which include stars below 40% of the Sun's mass, have time to fully mix their contents. They swap burned material out of the core and into the star's outer layers, while bringing fresh, hydrogen-rich material into the core. These stars, upon running out of hydrogen, won't get hot enough to fuse helium, leading to a state of slow contraction, ending in a white dwarf. But the highest mass stars, those born with 8 solar masses of material or more, follow a different path. They not only ignite hydrogen and then helium burning in their cores, but go on to fuse carbon, neon, oxygen, and then silicon and sulfur, eventually dying in core-collapsed supernovae. This process leads to a neutron star for the lower mass varieties and a black hole for the more massive ones. Here's where the puzzle arises with the Crab Nebula. There just isn't enough mass in the Crab Nebula, as inferred from these multi-wavelength observations, to explain its core-collapsed supernova and the resulting neutron star. The neutron star at its core, known as the Crab pulsar, weighs in at only 1.4 solar masses. Based on all the previous multi-wavelength data, we've been able to estimate the mass of the Crab Nebula, excluding the central pulsar, to be between 2 and 5 solar masses, though there is some uncertainty in this estimate. This presents a fascinating conundrum for astronomers to decode, adding to the myriad mysteries of our universe. However, observations at greater distances around the nebula, where it's plausible that a shell of material could have been blown off in earlier stages, reveal a complete absence of any detectable material at all. There's no shell, plasma, or diffuse gas that we can detect with our most advanced instruments. Even if we take the high mass estimate for the Crab Nebula, that still doesn't give us enough matter or material to trigger a core-collapsed supernova. This suggests a flaw in our understanding somewhere, but exactly where is a big mystery. Could we be modeling the nebula wrong? If so, improved data can help us better estimate the total mass of the Crab Nebula. Could we be measuring the mass of the neutron star incorrectly? It's possible, but not by that much. The most massive neutron star ever found is only slightly heavier than 2 solar masses. Could there be material that was ejected long ago that's now been blown away? Perhaps, but that doesn't align very well with our understanding of stellar evolution in the late stages of a massive star's life. Could we be misunderstanding the conditions for a supernova? It's unlikely, but we've observed so few in detail that we have to consider it. Fortunately, we're about to get some help from the full view of the Crab Nebula provided by the James Webb Space Telescope. This full-scale view of the Crab Nebula, from upper right to lower left, spans about 11 to 12 light-years in extent at the nebula's distance of approximately 6,500 light-years. The most significant new detail revealed by the James Webb Space Telescope imaging is the first complete and comprehensive map of the dust distribution within the Crab Nebula. Since the spectral features that reveal individual elements only apply to individual atoms, not to dust grains that may contain those elements, it's possible that we failed to sufficiently account for dust in previous observations. The central yellow, white, and green filaments that appear in the infrared image are dust-dominated, and could be incredibly rich in material. This could offer a new direction in our attempts to solve the mystery of the missing mass in the Crab Nebula. A case of cosmic detective work, if you will. Now, the images from the James Webb Space Telescope show what appears as grayish-white smoke filling in the interior of the cavity carved by the expanding gases.
Smoke? In space?
No, it's not smoke in the traditional sense. It's a phenomenon known as synchrotron radiation. This occurs when fast-moving electrons are accelerated by a strong magnetic field, and the magnetic field causes the electrons to radiate electromagnetic radiation.
And why can the James Webb Space Telescope see this and not the Hubble?
Good question. It just so happens that the wavelength range that the synchrotron radiation comes in matches the wavelengths that the James Webb Space Telescope is sensitive to.
And what about those smoke-like wisps we see on the outskirts of the nebula?
Those are curved and pinched, almost like they're being funneled into a central disc-like shape. One possible explanation is that there's a belt of dense gas confining where the supernova's winds can flow. This is another potential store of massive material that we may have missed previously.
But the nebula isn't just smoke and wisps, is it?
Correct. There are also hotter, heavier elements revealed by the telescope's observations, particularly on the outskirts of the nebula. The red-orange filaments of gas seen are doubly ionized sulfur atoms, which peter out at smaller distances than the lighter hydrogen atoms that Hubble was sensitive to, farther toward the nebula's outer edges.
And what about the heart of the nebula?
There, the smoke-like wisps located toward the center trace out the magnetic field lines created by the central pulsar, and you can see many curved wisp-like features all grouped together, indicating the locations where the magnetic field is strongest. Quite fascinating, isn't it? The images from the James Webb Space Telescope show material still being transported away from the central regions of the nebula, farther toward the outskirts. It's a fascinating view, revealing a variety of features that have never been seen before. But what's really interesting is the asymmetry of the nebula. The filaments appear to be lengthened toward the upper right of the pulsar, while simultaneously being relatively shortened in the opposite direction. The pulsar itself is moving in the direction where the filaments are elongated. So, perhaps the shape and extent of the nebula has something to do with the motion of the central stellar remnant.
So, the shape of the nebula could be influenced by the movement of the pulsar?
It's one possibility, but of course, further investigation is needed to understand this phenomenon better. What's also noteworthy is that the Hubble hasn't taken another look at the Crab Nebula since the early 2000s, that's more than 20 years ago. But that's about to change. Just as the James Webb Space Telescope is observing the nebula now, it's important to get simultaneous data from Hubble to paint a more complete picture of this fascinating region of the sky. Perhaps, with new, superior data from both observatories, we'll not only be able to map out the various details within it, but come up with a more satisfactory accounting of where all the mass is. The combination of a central pulsar, ionized plasmas, a wide variety of atoms, dust grains, heated gas, and expanding matter-rich filaments makes the Crab Nebula a spectacular sight and a scientifically rich place to explore the universe. It's an exciting time for anyone who wants to understand the end stages of a massive, but not ultramassive, star's life. After all, the Crab Nebula is one of the closest, best-studied examples in our own Milky Way galaxy. To summarize, we've been journeying through the marvels of the Crab Nebula, a remnant of a star that exploded in a supernova event recorded by astronomers back in the year of 1054. This massive star, once 8 times the mass of our Sun, collapsed and left behind a pulsing neutron star at its heart. Over time, the Crab Nebula has expanded and evolved, revealing enormous stores of gaseous material. Yet, the mass of the remnant pulsar and the ejected material still doesn't add up to the mass required to trigger a core collapse supernova. This is the cosmic mass mystery, and the James Webb Space Telescope is on the case, providing superior views and revealing new details. So, stay tuned, because as we get simultaneous data from the Hubble Space Telescope and the James Webb, we might soon have the answer to this celestial whodunit.
Absolutely, what a journey through the cosmos we've had. We hope you've enjoyed this deep dive into the Crab Nebula. If you're as fascinated by these space mysteries as we are, please make sure to blast that like button and share this episode with your friends.
And don't forget to leave us your comments. We always love hearing from you. Until the next deep dive into the universe, goodbye everyone.
Goodbye and keep looking up.
I got all this fascinating information from an article titled Jwst'S Crab Nebula, Can It Solve the Mass Mystery? By Ethan Siegel, published on Big Think on November 1, 2023. If you want to delve deeper into the subject, the full URL is in the video description. Now, I'm off.